In this video, I'll show you how to create a marble shader in Blender, fully procedural and without any external resources. I'll also go through how to organize your materials as to get the most out of them and to make them easily reusable by other users as well. If you're interested in the full shader, just check the link down below in the description. Before we do anything else, I strongly suggest that you travel to your preferences and under add-ons you make sure that the Node Wrangler add-on is enabled, since most of the shortcuts we will use do come from that. Now, a safe first step when creating a material is of course to look at some of its basic patterns, and to help with that, I gathered in this case a few references directly within Blender, ticking the fake user option at the top so that I do not need to reload them every time I restart the project. This reference here in particular will be, at least at this stage, our benchmark, so let's take a quick look at it. First, a sort of diffuse fine grain is separating the base color from what we could consider to be a first kind of color variation. Then, on a darker tone, we can observe more compact and elongated shapes that represent a first type of marble veinings, and within these veins, at their core, an even darker shade that I refer to as ridges throughout the video. In addition, a second type of veins, quite thin and even more compact than the first type, is running transversely across the material. These are the four main types of patterns we will need to get started with a base marble material, and with this in mind and with my cube ready, I'll just switch to the render shading mode. In case you want to follow along, I'm going to use for now the K-Bin HDRI coming from Polyhaven with a rotation of 4. The main tool we will employ throughout the pattern's creation process will be the Noise Texture node. With this selected, just hit Ctrl-T to automatically bring a Texture Coordinates node and a Mapping node in as well. At the end of the chain, a Color Ramp node with a bit of contrast will enhance the overall visibility of the pattern that we can preview by using the Ctrl-Shift and left-click shortcut. If we take a look at the parameters available in the Noise Texture node, we have Scale, which is quite obviously the frequency of the noise, while the Detail parameter is linked to the concept of noise octaves, which are essentially loops performed recursively by the software, with each loop returning an additional layer of details back, and that can be used to turn blobby shapes into more refined patterns. With Roughness, we can sharpen even more the peaks of the noise, and we will use that extensively. Finally, I'll leave linearity and distortion alone, since I won't use them in this specific occasion. What we have so far is sort of the typical, frankly quite boring kind of noise. And if we want to make it a bit more interesting, we first need to understand what is actually going on between the vector output of the mapping node and the vector input of a texture node. To simply put it, vectors represent a pointing tool in the 3D space, where by providing a value for each of the three axes, a system of coordinates is defined. In this context, color, which is also defined upon three values, the red, green and blue channels, can be used as vector data as well, in that each individual color channel will correspond to a specific orientation axis. Indeed, if we preview the output of the mapping node, we can already tell that it is expressing some sort of color information. To show this, we could split the output into the three individual axes and recombine them. Let's say now that we want to move the texture on the Z-axis, we could do so by placing any logical operator in between the Z I/O sockets. And this would be perfectly equivalent to splitting the output of the mapping node into the three color channels instead, recombining them again and performing the exact same manipulation we just did. This system though isn't really making our texture more interesting, as it only allows us to displace the pattern all at once. As such, I'm going to select all of these nodes and hit Ctrl-X to delete them, keeping the existing connections intact. The question would then be, how can we displace a texture at different locations on a pixel per pixel basis? To do that, based on what we gathered, we would need a rather chaotic color map. Well, it happens that the color output of the noise texture represents exactly that, which means that we can use it to displace itself. And this is the reason why in many procedural texturing tutorials you see something like this. And you can already tell how much more interesting the pattern has become. With the displacing noise texture node selected, we can use M to mute and unmute to clearly see the before and after. And this is really a method you can employ for a variety of material if you think about it, as it could be used effectively to mimic, among others, concrete, asphalt and so on. To complete the base chain, we need a couple of additional steps, and the first one would be to replace the color ramp with a map range node, which essentially can be used in the exact same way, but with the advantage of providing direct access to values instead of relying on pin markers. Now, the map range node comes with 4 values, and to show the way it works in relation to the more common color ramp node, I'm going to select the latter and reset it with the backspace key. The first value of the map range node is the equivalent of the black marker of the color ramp. When we push it toward 1, hence encompassing a wider range of grayscale values into our shadows, we are doing the same as taking the black pin, moving it to the right by the same amount. Similarly, the second value is going to work in the exact same way, but this time in relation to the white marker of the color ramp, which once moved to the left would result in an overall brightening of the highlights. The third value in the map range node is equivalent to the brightness or value of the black pin of the color ramp, which can be pushed from 0 or pure black to a brighter value, while the fourth and final value of the map range node can be used to manipulate the brightness or value of the highlights, similarly to what we could do with the white pin of the color ramp node. And when we switch between the two respective outputs, we can see that they are yielding the exact same result. At this point, I would remove the color ramp from the chain by pressing Alt and dragging the node away, and preview the map range node with Ctrl, Shift and left click, as well as reset it with the backspace key. The last step is to understand now which of the outputs of the texture coordinates node is better for our purpose. To clearly highlight the difference, especially between the generated and object texture coordinates options, I'm going to load within the shader a simple bricks texture set to box, and I'm going as well to reduce its styling a bit. The generated coordinates option defines a sort of bounding box around the mesh, with the origin set at its forward bottom left corner, which stands as a sort of 0 to 1 space, where the texture's density for a given piece of geometry is going to stay the same despite the scale of the object. The object coordinates option, on the other hand, places the texture's origin right at the origin of the mesh, but more importantly it allows to keep the material's look consistent among meshes of different sizes, which makes it generally the safest option, especially in scenes where the same material would be applied to multiple meshes. With that out of the way, I'm going to reorganize my chain a bit by creating different frames as to visually separate the nodes relevant for the texture mapping to those which belong instead to the pattern's creation process. Let's proceed by implementing a few tools as to control the different aspects of the pattern, starting from its contrast. What we could do is to trick it by altering the first two values of the map range node, but I usually prefer to have a single value to manipulate. Hence, I'll add a value node and I connect it to the first socket of the map range node, which is the one controlling the shadows of our pattern. And as I push the value toward 1, I would also want the highlights to come closer to the midpoint by the same amount, hence increasing the overall contrast. To do that, I'll need a math node set on subtract, so that I can indeed subtract from 1, which is pure white, my input value, to then connect the output to the first from max socket of the map range node. In this way, I can directly control the overall contrast with just this single input value. You can see that whenever I go past 0.5, the pattern plays in reverse, in the same way to what would happen if I switch the pin markers in a color ramp node. Since this is not going to be useful in our case, and while I still want the input value to range from 0 to 1 to make it more readable in general, I'm going to limit its output with a math node set on multiply, where I would in fact multiply the input value by 0.499, which is the highest available value before any pattern's inversion. In this way, moving the input from 0 to 1 will indeed move the contrast from 0 to the max. I'll group again these couple of nodes to make the node tree organized. Now, if we take a look at the pattern, we can see that despite the contrast level, the highlights are lying more in the upper range of the grayscale gradient than being actually white. And since this pattern will be used as a mask between the base color and our very first color variation, it means that too much of the latter would be exposed. We can limit this by pushing the fourth value of the map range node, which represents the brightness or value of the highlights, to something greater than 1. And again, to control it, I'll use a value node set for the moment to 1.5. Another point is that when we decrease the contrast to the minimum, we can clearly see that still a bit of variation is going to be applied. We need then a sort of influence parameter that we can use whenever we want to zero out the mask entirely, which can be achieved by bringing the brightness or value of the shadows up to the same brightness value of the highlights. In nodes, this is equivalent to adding another value node to be used as an input parameter and multiplying it by the value we are using for the brightness of our highlights, connecting the output to the relevant socket of the map range node. But as this is currently doing the opposite of what we need, with 0 being full influence and 1 being no influence at all, we actually need to feed the multiply node the complement to 1 of our influence input value node, which will now make the system work as intended. Again, I'm progressively grouping nodes by their functionality as to keep track of what is doing what, as these trees can get pretty busy quite fast. To get control over our pattern, we could either switch the noise texture node to 4D, which means that apart from the 3 axes, we would also have this fourth additional W parameter, or, and I'm going to choose the second method, we could input a vector into both the location and rotation sockets of the mapping node, which would allow us to control the pattern on an axis per axis basis. In a similar way, I'll use another vector to control the overall scale of the pattern as well. We can now further improve the organization of our material, and as such, I'm going to select this bunch of nodes and I'll hit Ctrl G to create a group, and we can then use Tab to go in or out of the group itself. I'll then rename it to something like fine grain, and within the group, in the group palette on the right, I would rename its output to fine grain mask and its vector input to texture coordinates. Now, as I want to have control over a few aspects of the pattern from outside of the group, I'll need to create additional input parameters. I'll start from the influence parameter by replacing the corresponding value nodes with a value coming from the group inputs, which I rename to fine grain influence, and I'll do exactly the same with the contrast. And since we spent time to build them as 0 to 1 sliders, I'll also change the subtype to factor with a min of 0 and a max of 1. If we tap out of the group, we can see how much more handy this is becoming. So let's continue the process, and from within the group I'm going to define input parameters also for the pattern and the scale of our mask. Here you could decide whether to have a distinct parameter for each single axis, as it will be the case for the veins pattern, or instead use a single parameter for all of them. For a fine-grained mask, I think this second strategy is more than enough. For the moment, I would set the pattern to 0, the scale to 1, and the contrast to something around 0.86. There is one additional parameter which is going to be of great importance. From within the group, the roughness value of the noise texture node used to displace the other noise texture node can be used in fact to define how much the pattern is going to be spread apart, with lower values corresponding to more compact shapes. And this will be essential when creating our first proper veining pattern. I'll connect it then to a new group input parameter and I'll rename it to fine grain spread, leaving it for now as high as 0.8. With our first pattern ready, it is time to start creating our material for real. As a base, I'll use a UV sphere with 2 levels of subdivision, I'll apply to it what we created so far, and I'll bring the roughness down to something like 0.1 to make the sphere look nice and shiny. Now, the output of the fine-grained pattern will be used to mask the first two color variations. If you're used to layer-based systems, you probably know that the white portion of a mask reveals the current layer, while the black part is going to reveal instead the layer underneath. Hence, you may be tempted to think that the current layer corresponds to the top socket of the mix color node, while the underneath layer corresponds to its bottom socket. Actually, it is exactly the opposite. So, the base color, which will be visible in the white portions of the mask, needs to be placed at the bottom, while the color variation, driven instead by the black parts of the mask, will be at the top. To create the second pattern of the material, which will be our first type of marble veinings, I'll leverage on what we already have and just duplicate the fine-grained node. You can see that there is a little number to the right of the node's name, which basically tells you how many times that item is currently used within the project. The two groups are hence at the moment linked to each other. To make the second group a unique and distinct item, it is enough to click the number here and you'll notice that the name will change to finegrain.001 to distinguish it from the first node group. I'm going to rename it to something like primary veins, and I'll use it again as a mask by adding another mix color node to the chain and feeding the new group's output to the factor socket. I'll then rename the spread input parameter in both groups as scattering, since it makes more sense, and in the process I rename each input-output of the second group as well, coherently with what they represent. I'll then make another couple of changes to the primary veins group. First of all, I want to have now a distinct parameter for each one of the axes of the scale vector, as this will be useful when building specific patterns, and I'm also going to bring the scattering down to something around 0.55, as to create this kind of elongated and swirly shapes that do mimic quite well marble veinings. For the color, I'll choose a slightly darker tone than the one used for the fine grain, and I'll eventually bring the roughness down even a bit more. Now, this is starting to look like something, but we still need to push it a bit farther. In particular, I want to expose some of the darker regions of the veining pattern to be used as an additional mask for color variation. To do that, I'll add another map range node at the end of the chain and I'll connect it to a new group output which I'll call Ridges Mask. I'll then add a new mix color node to the main tree using the Ridges output as the factor. At the moment, I'll select a bright blue color to clearly highlight where the mask will be applied. Within the node group, I'll restrict the first two inputs of the last map range node to something like 0.1 and 0.15, which means I'm only selecting the very dark spots of the base pattern. And again, I'll create a value node to control the brightness of the highlights and build again a system to get control over the general influence of the new mask, just as we did before for both the primary veins and fine-grained patterns. Lastly, I want some control over how far away the ridges pattern is spreading out, and as such I'll define a suitable interval, which in this case could range from 0.15 to 0.75, to be then controlled through an input parameter which I want to range instead from 0 to 1. In such cases, the logic is to simply subtract the two values of the interval, multiply the output by the input parameter and add back to the result the lower boundary. I can then replace the placeholder value nodes with input parameters to be controlled from outside the node group with the proper names and properties, test it out, and finally select a suitable color variation, which may be just a darker tone with respect to the one used for the primary veins, or even the base color in case we want to add a bit more contrast to the final output. The final step in creating the base patterns for the material is to work on the secondary type of veins. For this, I'll use a Voronoi texture with the coordinates coming again from the main texture coordinates node. I'll change the type of noise to distance to edge, which will give me this kind of fractured look, and I'll use again a noise texture in between the mapping node and the Voronoi to create some distortion. Also in this case, the roughness parameter of the noise texture node will play a big role in defining the overall shape of the pattern, and for the moment I'll keep it to something around 0.5. With a map range node at the end of the chain, I can once again have control over how the secondary veins are spreading over the mesh, either being some very thin lines or otherwise increasing their thickness and reach. The math behind this should be pretty obvious at this point. What's interesting here though is the concept that apart from building patterns, it is also very important to learn how to break them. With the double noise texture combo we already used a few times, I'll create another black and white mask to be then mixed with the output of the Voronoi, and the aim here is to break the uniformity of the latter and to try to achieve a more disconnected kind of look for the lines that are representing the veins. I'll then test the mask through an additional mixed color node, playing around with the parameters as well as with different potential color tones. Of course, I'll rearrange this last node tree into its own separate group, renaming each I/O parameter accordingly and creating the different input parameters to be used from outside the group, just as we did before. And for the basic patterns, we should be good at this point. The next step is now to complete the shader with a proper set of controls for the roughness, and we will also need to talk about another very important feature when dealing with CGI marble in general. In addition to that, there are still some major improvements we can do on the organization of the whole node tree. First of all, even if in an unaltered state of condition, we may want to avoid having a single uniform value controlling the roughness of the material. To deal with this, we can use the node structure we are at this point familiar with to create some sort of grayscale pattern, where the last value of the map range nodes could be used to drive the overall roughness value of the material. With this system, we are essentially retaining a non-uniform pattern which will add just a bit of extra flavor to the final output. I'll organize this simple node tree in its own separate group once again, and I'll create as well the base roughness input parameter to be used from outside the group. Let's give this a quick test and we can see that it is working as intended. I'll leave it for now at 0.3 and we can start dealing now with the organizational aspect of the base material node tree. The first thing that we can do is to place all of the mixed color nodes into their own group. The output of this will be of course the albedo of the base material, and I would suggest renaming the mask inputs even if it is not needed to make clear what each one of those will do. Beside that, I will also create input parameters for the base color and the different color variations since I want to access them from outside the group. And here I would say that renaming each input parameter is essentially a must as to avoid confusing users in general or even yourself. With the albedo node group in place, we can finally create the upper layer of the base material by selecting everything apart from the texture coordinates node and by creating yet another group. This will be the actual layer to be used when tweaking the different parameters of the material. To keep it organized, I use this rather new quality of life tool which has been recently implemented for shaders and which consists in using panels. From the group subpalette on the right, just click the plus button and choose panel from the drop-down. Panels are essentially containers that can be used to group input parameters based on whatever logic you wish to apply. In particular, I start by creating a base parameters panel where I will put the base color and base roughness inputs, and we can already see how this is going to play out in the controlling layer. Now, if you have spent the right amount of time making sure that all of your input parameters do have the proper names, it will be here just a matter of connecting sockets and deciding which input parameters to promote to the final outer layer. In my case, I'm going to add them all, but you may want instead to leverage on this layer system and have just the basic controls in the outer layer as to keep it light and readable, while keeping maybe the less commonly used parameters buried a bit deeper into the layer system. We can now test the system we built so far and explore as well its versatility in creating different types of patterns. For this purpose, I'm going to switch to a different reference image on the right, focusing in particular on this slab of one of the finest types of marble in the world, coming directly from the Italian extracting site of Carrara. I'll change the HDRI to something different, and as a first step I will simply zero out every influence parameter as to play for the moment just with the base color and its fine grain variation. The process is quite simple. I'll use the reference to sample colors, while I'll progressively enable the different layers one by one, manipulating the respective parameters as I go. One of the advantages of using the object option in the texture coordinates node is that, well, we can actually use an object to define the orientation and scale of the patterns as a whole. As such, I'll add an empty to the project and I'll target that empty from within the texture coordinates node. In this way, by simply rotating the empty and by scaling properly along the relevant axis, we can mimic the diagonal orientation of the original veining pattern in the reference. I'll apply the same concepts also to the ridges and to the secondary type of veins, and it will be then just a matter of playing around with the different parameters until we reach the desired result. To complete the base shader, we need one important extra step. Marble, in fact, is a translucent material, which means that light would penetrate its surface to be then scattered irregularly at different points in space, and then exiting back at a different angle than the one that would be implied in just a simple reflection. To prove the point, I loaded into the scene the model of the bust of one of the 5 good emperors, Antoninus Pius, and I created a simple white version of the base material, retaining just a tiny bit of color variation from the veinings patterns. I'll hit F11 to make sure that I'm positioned over the first render slot, and then hit F12 to get the first render, being the one without any subsurface scattering applied. I'll then switch to the second render slot, and with that done, I would go back to the principal BSDF to open up the subsurface palette. Here we have a few controls. Weight will allow to transition from a no subsurface state to a full subsurface one with any value in between. Scale is going to define how far light would travel into the surface in general, while radius represents how much of that distance is covered on a channel per channel basis. In this case, I would reset the vector to a simple neutral color. Lastly, anisotropy will control the directionality of the scattering, and for this example I leave it to 0. Time to hit F12 again and wait for the render to complete. Subsurface scattering is quite demanding and can increase render time significantly, so make sure that you handle it with care based on the context and the level of details required by each specific shot. When comparing the two results, it is pretty obvious that in the first case we got something which is actually more similar to a glossy ceramic material, while in the second shot we are definitely closer to what marble should really look like. To integrate the subsurface scattering into the base material, I use a mixed color node with both pure black and pure white colors, where the factor between the two will be a substitute for the weight parameter of the subsurf in the BSDF node. And we will see in a moment the reason why I decided to set it up in this way. Marble indeed is exposed as any other material to a certain degree of degradation. Either dirt or flaking or some chemical reaction due to external agents, these alterations will have an impact on the different masks or outputs of the base material. As an example, I'm creating here a node system based on the same techniques we already explored to reproduce the effect of the rusting in time of the minerals contained within the marble veins. What is different here is that I'm using the concept of spread as opposed to that of contrast when defining a pattern. Within the map range node, I'll bring the first two values both to 0, and by manipulating the shadow's brightness, we can recreate this idea of the specific alteration progressively taking over the mesh. I'll then simply organize the nodes as to expose the controlling parameters as usual, and I'll proceed on to affect the different components of the base material. For the albedo, the mask can be simply used as a factor once again, and we can also in this case leverage upon our references to sample the right color variation. It is with the roughness indeed that things become actually more interesting. As the rusting is supposed to be less glossy than clean marble, and being the rusting portion of the mask expressed in white, we can use a mixed color node to connect the output of the rusting mask to the bottom socket, change the blending mode to screen, and now the factor value of the mixed color node will represent how much more rough rusting will be in relation to the base material. In a similar way, we need to address subsurface scattering as well, since rusted material do not have any translucency. In this case, we need to subtract from the original weight mask of the subsurf, and to do so we can invert the output of the rusting mask and multiply it on top of the weight mask as to remove those rusted portions from where the subsurf is eventually applied. Here it is instead the node tree I ended up using for the dirt layer. One tip is to use the ambient occlusion node as to make the effect kinda smart based on the specific mesh's geometry. Just remember to enable this only local option to keep the layer from being affected by surrounding objects, unless of course that's your desired outcome. Ambient occlusion will be one of the sources driving the positioning of dirt, and again it is important to remember to always employ a system to eventually break the uniformity of the generated pattern. Along with that, I'll also have a non-ambient occlusion source, this time obtained using a Musgrave texture, which is then mixed back with the AO output, where the idea is to retain the ability to control the influence of both sources independently. When it comes to flaking in general, I prefer to have two distinct patterns. One to represent a sort of diffuse fine wear, for which I'll use the double noise texture technique, and the other to be used instead for cracks, for which I leverage again on a system similar to that used for the secondary veinings. To affect the normal map, we have a couple of options. The first one is to mix ahead the two patterns and then feed the mix into the height socket of the bump node. This method though does not provide full control over the normal strength for each pattern. And a solution to that would be to have instead two different bump nodes for the patterns to be then mixed with a mix vector node where, and this is important, the output of one of the two patterns needs to be used as the factor. In this way, we can control the normal strength of the two patterns independently to achieve different looks. This is the complete shader I created based on the concepts shown in this video, just with a few more parameters as to make it versatile enough in creating virtually any kind of marble pattern we may think of. If you're interested in the full shader, remember to check the link down below in the description. Thanks for watching and see you next time.